David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to catch up with notes or write down some questions. Third, you can turn on the captions and read my words on the screen. Today's lesson covers derivatives and how we use them to find the slopes of various tangent lines. So before we jump into that, I just want to review the power rule, which is what we're going to be using for this lesson. Power rule is over here. It just means if f of x is some coefficient times x to some power, to get the derivative of this function, you just take the n, multiply it by the coefficient to x, and then reduce the power by 1. So that's our power rule. And that looks pretty simple. There were some complicated situations with fractions and stuff like that, but basically that's the rule you apply to find the derivative of any function. Okay, so today what we're going to do is we're going to find the slope of lines that are tangent to various functions at certain points. So check this out. Here's our function. F of x equals 3x to the 4th power. Find the slope of the tangent line at x equals 1. So x equals 1 is a point that's on that function. Okay? In fact, we can plug it in. We know that 1 to the 4th power is still 1. So that point is really 1, 3. But we're not going to need the 3 in this. We just need the 1. Okay. So there's a line tangent to this function when x is 1. We want to know what the slope of that tangent line is. Now, if you recall from our last lesson, the derivative function of this function gives us the slope of any tangent line if you know the x-coordinate that you're after. And we do. They're telling us that right away. First step, take the derivative of f of x. So f prime of x is going to equal 4 times 3 to the x 4 minus 1. I'm just applying our power rule over there to this function, and that's going to give us 12x to the 3rd. Okay? So that is the function that we can use to find tangent line slopes. So to find the slope when x is 1, we just plug 1 into the derivative function, and that's f prime of 1 equals 12 times 1 to the 3rd power is going to be 12. So the slope, which we usually use little m, is 12. That's how to do that. Okay, let's do that again, but now with a slightly different, perhaps more complicated function. So here we go. F of x is now 2x squared plus 3x minus 5. Very typical quadratic equation. So we want to find the slope of the line that's tangent at the point where x is 1. Okay? We know that's a parabola, so somewhere in there it's curving. At x equals 1, there's a tangent line, and we need to find the tangent line slope. So, see if you can pause the video, do the power rule on that function to get the derivative function, put that here, and then plug 1 into the derivative function and get the slope of that tangent line. Okay, so check this out. F prime of x is just 4x plus 3. Remember this, we multiplied the 2 by 2, that's 4. 4x, reduce that by 1, which is just x to the 1, which is just x. This is x to the 1, 3x to the 1. Multiply the 3 by the 1, and this goes to x to the 0, which is just 1. So this one ends up being 3. Finally, the 5, remember constant, when you take the derivative of constant, it goes to 0, so there's nothing there. So here is our derivative function, 4x plus 3. Then we take our x-coordinate of the point where we're trying to find the tangent line slope. We plug it into the derivative function. Derivative function gives you slopes of tangent lines, and we plug it in. So 4 times 1 plus 3. I don't know why I wrote 4 there, because the answer is going to be 7. And 7 there as well. Let's take a look at this situation graphically. Remember, all these things are graphical. We're talking about tangent lines and functions. So what I did is I went ahead and graphed this function. It's a parabola with a y-intercept of minus 5 and an x-intercept of 1. And so what I want you to do copy that down in there, and then think, maybe grab a different color and draw that tangent line on there, and then confirm to yourself that the slope should be 12. Remember we did that, and I'm sorry, the slope was 7. Right? I thought it was 4, then I thought it was 7, and that 7 is what it is. So the slope of the tangent line is 7. Pause the video, sketch your tangent line, and come right back. Okay, so my tangent line is not perfect. I didn't quite get it to touch the point of tangency, and the main problem there is that my curve of my parabola is kind of mostly straight. But I think you can see what's going on. If you wanted to make a little bit better picture, there's your curve, and here's the point of tangency, and then the tangent line would do that. And so it just touches the curve, doesn't cross the curve, and so on. So, slope of the tangent line should be 7. Yeah, I mean, I think maybe the way I've drawn it's a little bit more than 7, but it's pretty steep. And 7 is actually a pretty steep slope, so that confirms our calculation, and it also shows you what we're doing. So again, here's our function listed there. We found the derivative function. We plugged x equals 1 into that derivative function, and we got a slope of 7. And then I sketched my function. I drew my tangent line at the point 1, and it confirms, yeah, that looks about right. All right, let's get a little bit more complex and answer a few more questions about our function using the derivative to do that. So here's my prompt. Here's an f of x, quadratic in vertex form. Show intervals over which the function is increasing and decreasing. So we know this is a parabola. We know it opens up. So the left limb, the function is decreasing because it's got a negative slope. And on the right limb, the function is increasing because it's got a positive slope. Now, there's a couple ways you could do this. You could just graph it and take a look at your graph. That's fine. But we're going to do this with the derivative so I can illustrate exactly how this works. And then we'll do a more complex example. So, first off, find the derivative. And you're going to have to expand this and do all that algebra before you take the derivative. So go ahead, pause the video and do that. Okay, so I expanded it by first expanding my binomial. So x plus 3 squared ends up with x squared plus 6x plus 9. I factored in my 2, multiplied that out, and then I subtracted my 2 from my constant term, and I end up with plus 16. Then I took the derivative of this term, and there's my derivative function. So the easiest thing now is to go to your calculator, put the derivative function in and the original function in, and then you can use that to determine the answer to this question. When is the function increasing and when is the function decreasing? So go ahead, give that a shot and come right back. Okay, here's my graph. I did this in Desmos. I wanted to put it on the board just to give it a look-see on the board. You should be looking at your calculator while you're going over this to make sure you can read the values you need to find. So, blue graph, that's my function. That's my original function. Red graph, that's my derivative function, going like that. Now let's do some interpretations. Vertex, -2, -3, we get that out of here. So I plotted that. The intercepts are at -1, -4, got that from Desmos. And then this one, I have an intercept of 12, and then my slope is 4. So that gets me crossing the x-axis at the point -3. Now, check this out. When the derivative is negative, the function is decreasing, and so that's this interval. And when the derivative is positive, the function is increasing. And that lines up perfectly. See how the vertex is at -3, and our derivative function crosses the x-axis at -3. So at -3, you're at the vertex. So the derivative function is positive. So that way from -3, the function is increasing. And then once it crosses the x-axis, the derivative function is now negative. And sure enough, our parabola is decreasing there. So we can write the intervals like so. I and c for increasing, set of all x such that x is greater than -3, and decreasing would be the set of all x such that x is less than -3. Okay, so x can't be 3. Why not? Tell me the answer to that. Okay, it's because the derivative is neither increasing or decreasing. The slope is 0. It's doing nothing. It's got a horizontal line, so it's flat. There's no slope, or the slope is 0. One last one, a little bit more complexity. Check this one out. We have a cubic function. We've got a third power. So our function is 2x to the third plus 5x squared plus x plus 2. So we want to find out the intervals over which this function is increasing and decreasing. And if you remember, cubic functions have a habit of doing something like that. So we're going to get some interesting intervals. It could also be like this. Okay, so you're going to get, on this case, you have 2 increasings and 1 decreasing. So the derivative would be positive during these 2 intervals and negative here, or the opposite way if the function is going like so. Regardless, what we're going to do is we're going to find the derivative function of that one, and we're going to take both functions, and I'm going to step over to Desmos, and we'll look at them there, because making this graph on the whiteboard gets a little messy. So, pause the video, take the derivative of that function, and come right back. Okay, here's what I get. This one goes to 6x squared, this one goes to 10x, x goes to 1, and the 2, the constant, goes away. So now, while I step over to Desmos, what I want you to do is put these in your calculator. And really, you could use Desmos, but your calculator right now is what's allowed on the test. So I would say get the practice on your calculator. Remember, in our class, the calculator is permitted for all sections of the test. So this should be your go-to. So like drawing out the graphs, or there's other techniques for finding out this information, but they're no calculator techniques, and they're kind of complicated. You have a calculator for everything, so make it your go-to. Okay, here we are in Desmos, and you can see on the upper left here, I have put the original function, our cubic function, 2x to the third plus 5x squared plus x plus 2. And you can see it does this zigzag here. So the function is increasing. Tangent line slopes are positive all along here until we get to this local maximum. And then tangent line slopes are going to be negative until we get to the local minimum. And then finally, again, tangent line slopes will be positive. So what that means is that all the way up to the local max, the derivative function is going to be positive because the function is increasing. And then between the local max and the local min here, the derivative function is decreasing because the slope of the tangent line is negative. And then again, from this local minimum on up, the derivative function needs to be increasing, again, because the slopes of the tangent line are positive. So what I'm going to do is, first, I'm going to turn on over here again on the left. Now I have the derivative function typed in there, all ready to go, and there's that parabola. Now, it's a little hard to analyze this. You can see the points do line up right here, where the derivative function goes from positive to negative. That coincides right with this local max. So when the derivative function goes to negative, the parent function, the original function, is going to change from increasing to decreasing. And the same thing at this point, it lines up exactly with the local minimum. So I'm going to turn off the original function so we can hone in on what we need to say. The question was, what are the intervals where the original function is increasing or decreasing? So what that means is find the intervals where the derivative function is positive and negative. So all the way to this x-intercept right there, which is minus 0.555, the function is increasing. The original function is increasing because the derivative is positive. Now once we pass this point, and from here all the way to this other point, the original function is decreasing. And you remember, that's the jag on our cubic function. So that's when the jag is going back down. And then finally from this point, minus 0.10685, the original function is then increasing again because, again, our derivative function is positive. So when you put this in your graph, really all you need is to put in the derivative function and look where it's positive and where it's negative. And that will tell you where the original function is increasing or decreasing. So there you go. Thanks for watching the video. We'll see you in class. Now that you've watched the video, take a minute to jot down some notes, some questions, or a quick summary of the lesson. You can also re-watch portions of the video that were a little bit challenging the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.